Hello, I'm David Shin, and this is the Lab 2 report for Physics 1. So this lab was intended to track the position of an object moving in projectile motion. This object moves in the two-dimensional plane with only x and y changing, and we compared the observed position with two theoretical models generated in GlowScript. The object we used was an X-ray marker. Position data was gathered through Tracker, and we used GlowScript to generate a model. This lab involves basic kinematic equations along with Newton's second law. So Newton's second law states that net force is equal to the change in momentum divided by the change in time. And other equations we used are some of the basic kinematic equations, such as the velocity update and the momentum update, as you can see on the left. And so in the lab, we assumed two cases. One where the only force acting was the force of gravity, and one where there was a drag force and a force of gravity. The model was generated in GlowScript using a line of best fit from the data from Tracker. We found the measured position change for the actual data was greater in both the x and y direction, which is due to errors described later. The previous equations can be used as there is a velocity affected by force, meaning it can be modeled with just the force and velocity equations, and the object follows the basic laws of kinematic equation. The system is the x-ray marker, with the surroundings being everything else, such as the ground or the air. So here's the position data. We start at 0.0171 meters and 0.512 meters, and time equals 0.267 seconds. So you can just see in this clip, this is how the marker moves, and that's how the data is structured. And so to find the initial velocity, we took our first two time steps, and then we subtracted them over that interval of time with a position on top. And that was how we were able to find the initial velocity in x and y. As you can see here, we took both these 2 points and these 2 points respectively and took them over this time interval to find our initial velocity. So here's a generated model. For the first case, F net was equal to Fg, and then the second case, F net was equal to Fg plus Fd. And so within the models, our time step was actually a lot smaller to generate more accuracy, and the mass of the marker was 0.015 kilograms. And so you can see here that we have the time intervals here from here to here, and we have how the force net is updated with the gravity force and the drag force. And you also have the initial conditions up here and the mass. And so here are the graphs. This is the recorded data. As you can see, it has a much greater change in x. Same over here with the y. As both the models are very similar, the one with drag obviously has a slightly smaller distance traveled due to the resistance of drag. So some sources of error, we could have had errors rounding in the calculations or time steps, as the model had a much more precise time step, as its time step was 0.01, as the recorded data in Tracker, whose time step was 0.034. The initial step size difference also could have caused the first step size to be much greater due to the initial burst of speed, or much smaller, as the actual data shows a much greater increase and the model data shows a much smaller increase. So this could have skewed both the starting conditions, which could have led to that disparity in the final distance traveled. And as I said before, kind of following up on two, measured position change in the x and y directions, the marker could have had much less drag in the x and y direction in the actual data than the model, as I used a b that made both positions close to as accurate as possible. So I was trying not to skew either x or y distance traveled, which could be why both are significantly smaller in the model with drag than the actual recorded data in Tracker. And so if there was basically this terminal velocity, so this is with no drag, this models it pretty accurately on the theoretical concept of projectile motion, as the y velocity here decreases linearly according to the force of gravity, and the x velocity stays constant, which is what we discussed in class regarding projectile motion. And then this is with drag, so this also makes sense. The x velocity kind of decreases as the velocity of the projectile increases, and the y velocity also does that. It's a bit skewed here, as you can see, but that could be due to the errors in the b value or the initial velocity. It would make more sense if this velocity graph was over here, as the y velocity increases at a much higher rate than the x velocity. So the graphs should be switched. And so if the object were thrown straight up without drag, the time would be the same due to equation 4. This equation right here, if they're changing the same distance, the velocity is the same in the x direction, so overall time is the same. And with drag, it would also be the same as well to the actual data, as it's the same overall force and the same initial speed. It's just the magnitude distributed along a different vector. In this case, it would be the y vector. And thank you.